unitary induction. So that we discussed in the last class. So these are used for reducing the dimensions. Okay, and the next one is a numerosity reduction. In case of numerosity reduction, we are representing the original data in smaller forms. In smaller forms. In other way, we are representing the data. That is numerosity reduction. So according to this, we have different techniques. One is regression. So regression, what it does is it will convert the entire data into a model, a simple straight line equation model. So yeah, that is the one technique for numerosity reduction. And next is histograms. So this is also one more way for numerosity reduction. Okay. So a histogram, yeah, a histogram for an attribute A. So it partitions the data distribution of A into disjoint subsets, and each subset is referred as a bucket or a bin. The data will be distributed. The data of an attribute will be distributed and divided into different subsets, disjoint subsets. Disjoint subsets means the element in one set will not be present in another set. The same element will not be repeated. That is disjoint subset. So and each subset is referred to as the bucket or bin. So if each bucket represents only a single attribute value frequency pair, then we refer that bucket as singleton bucket. I'll explain you this singleton bucket with an example. Okay, so let us consider this price attribute in our all electronics database, and these are the prices of the items commonly sold. So these are the prices in dollars. Yeah, first we need to sort all these attribute values. So $1, $1, $5, $5. So all these are the items prices. The items prices in dollars. Now we are going to represent these attribute values in another form called histogram using this singleton bucket. Yeah. Yes. Considering that data, whatever the data we have considered in the previous slide, so for every attribute value, we'll find out the frequency. For example, here 1. How many times it occurred? What is the frequency of 1? 2. Frequency of 5 is 5. Frequency of 8 is 2. So frequency is constructed. Frequency of 1 is 2. Frequency of 5 is 5. Frequency of 8 is 2. So for every attribute value, count is calculated and then it is plotted. So this is the histogram for price using singleton bucket. Means each bucket represents So each bucket represents one price value frequency pair. One price value frequency pair. So if you consider any bucket, so this is bucket 1, bucket 2, bucket 3. If you consider any bucket, for example, bucket 15. So it consists of count value as 6. So value frequency pair is considered. Only one value is considered here. Only one price value is considered. So these kind of buckets are called singleton buckets. If you construct the histogram using this singleton buckets, it looks it looks in this manner. Okay. For every unique value, we are constructing it. We're calculating the count and then drawing on the graph. See, equal width histogram. So this is one more way of creating the histogram. This is equal width histogram for the same data price. Here the values are aggregated so that each bucket has a uniform width of $10. So if you see the list of prices, they are from 1 to 30. They are from 1 to 30. So they have considered a width of 10. So how many buckets will be there? Total 1 to 30. 30 by 10. That is 3 buckets. So every bucket having the equal width of 10. So So 1 to 10, 11 to 20, 21 to 30. So 1 to 10, what is the frequency? We'll just count it. 1 to 10. What is the frequency? 2, 13. So 1 to 10, the frequency is 13, somewhere here. Similarly, 11 to 20, we'll find out the frequency and then mention it. Similarly, 21 to 30. So this is not the singleton bucket. This is equal width buckets. Yeah. So partitioning rules to determine the buckets. We have equal width. In this equal width histogram, the width of each bucket range is uniform. Equal frequency or equal depth. This is, we create the buckets in such a way that the frequency of each bucket is constant. The frequency of each bucket is constant. For example, so here the frequency of this bucket is 13, frequency of this bucket is some 24, frequency of this third bucket is somewhere around 40. So if you consider this equal frequency bucket, we'll partition the data in such a way that the frequency will be same. The frequency, this height of this histogram, whatever we have drawn, it will be same. The frequency of each bucket will be same. So that is equal frequency or equal depth. So that is one way. Creating histogram is one way of converting an attribute into some other form, attribute data into some other simpler form. The next technique is clustering. So this clustering technique, what it does is it groups the similar data. It groups the similar data. So they'll partition the entities or objects into groups so that all the objects present within a cluster are similar to one another and dissimilar to the other objects in the other clusters. So how this is used for data reduction? Yes, after creating the clusters, means after grouping the related data, we'll select one representative from each cluster. One representative. For example, if a cluster consists of some 10 objects, then among those 10 objects, we'll select one as the cluster representative. So the cluster representations of the data are used to replace the actual data. So in this data reduction technique, for example, you have some 1,000 rows of data, 1,000 entities information. And now if you create the clusters, for example, you got 10 clusters. Based on the features of that object, you have grouped them using any clustering technique. Then, for example, you assume that you got 10 clusters. So among that 10 clusters, so from every cluster, one representative is considered. So now, how many representatives will be there? 10 representatives. Okay. So in that way, this 1,000 tuples of data is represented in simple form with 10 cluster representatives. Okay. So that is usage of clustering in data reduction technique. And one more is sampling technique. So it allows a large data set to be represented by small random data samples. For example, if you have a data set with n tuples, okay, so you are having a large data set D containing n tuples, then these are the sampling techniques. Whatever I mentioned here, these four are the sampling methods. So one is simple random sample without replacement. The sample size is yes. Out of n tuples, how many you are selecting? Yes samples. You are randomly selecting the samples. This is created by drawing S of the total n tuples, where S is always less than n. And what is the probability of drawing any tuple out of n? It is 1 by n. Okay, the probability will be 1 by n. Means all the tuples are equally likely to be sampled. There is a chance equally for all the tuples. So among n tuples, you are selecting randomly S number of tuples. So this is without replacement. So once you draw that particular tuple, then it is kept aside. Means it will not be considered for the next round of sampling. Okay. So yes, number of times you're collecting the tuples. So for the first time, if you select one tuple from these n tuples, then from the remaining n minus 1 tuples, you are going to select the next tuple. And in the next round, from the remaining n minus 2 tuples, you are going to select the third tuple, like that. Okay. So, but the second technique is simple random sample with replacement. This is a we can understand it from the name itself. Once you draw a tuple from n tuples, again for the next round, we'll consider the previously drawn tuple for the second round. Okay. So that is, after a tuple is drawn, it is placed back into the original data set D so that it may be drawn again. So here there is a possibility that the tuples considered for sampling may be repeated. Okay. Next one is cluster sample. So here among these n tuples in this data set D, we group them into m mutually disjoint clusters. We'll group all the tuples present in D to m disjoint clusters. And then we'll apply this random sampling technique. Random sampling technique is applied on the clusters. We'll see in the next slide with examples. You'll better understand there. Yeah, Shubham is asking a question. In which replacement sampling, how do we know when to end the sampling process? So the number of samples is considered, right? Yes, number of samples. Yes is the input. So the iteration process repeats S number of times. Is it clear, Shubham? Yeah. And next, the fourth one is stratified sample. So here, if D is divided into mutually disjoint parts and each part is called as a strata, now a stratified sample of D is generated by obtaining a simple random sample at each strata. Okay. So I'll explain these four with examples so that you'll get an idea, difference between each technique. May be confused with cluster sample and stratified sample. So if you see this example, you'll understand. Yeah. So this one is SRSWR, random sample without replacement. So if this is the input, wait for it, right? Yes. If you consider this as D, the data set D with n is equal to 8, n tuples. So what is S value here? S is equal to 4. So in this first technique, you're randomly selecting from 1 to 8 without replacement. So among these 8, first you selected randomly and you got T5. For the second round, you will not consider this T5 again. This is not considered for the second round. And now among T1, T2, T3, T4, T6, T7, T8, you'll select one more sample. You got it as a T1. So the remaining T2, 3, 4, 6, 7, 8. So you got T8. The next round we'll consider among 2, 3, 4, 6, 7. Now you got 6. Okay. So this is a simple random sample without replacement. You're not replacing this again to the input. Okay. Yeah. And next, the second one, simple random sample with replacement. So among these n tuples, first you randomly selected and you got T4. And in the next round, we'll consider T4 also. So every iteration will consider the samples from T1 to T8. Okay. So first time we got a T4 and next time we got a T7. Third time we got T4 again. because you're selecting T4 again with replacement. You replaced T4 again here. So for the third time, if you consider, we got randomly T4 again. Next, T1. So this is the second technique. Coming to this third technique, here we considered some 1,000 tuples. 1,000 tuples. Now we have created the clusters in such a way that we have clustered these 1,000 tuples, and for example, T1 to T100 are considered as the first cluster, and T101 to T200 is considered as the second cluster. So on T9012 to T1000 is considered as the last ninth cluster. So among these clusters, I am randomly selecting. Yes is given as 2. So 2 clusters are selected. Okay, so 2 clusters are selected. So yeah, if I select, I got this second cluster, and this is seventh one. You are grouping the data, and then after forming the clusters, you are randomly selecting the data from those clusters. So this is a cluster sampling technique. Okay, and next one is stratified sample. So based on the attribute values, we'll group the data. Based on the attribute values, we group the data. So here you can see this is related to age. So stratified sample according to the attribute age. So if age is having 3 kinds of values, youth is one value, middle aged is the second value, senior is the third value. Okay, so each one is called as one strata. So first strata, second strata, third strata. Now you're randomly selecting from these records or tuples. So if you select from this, randomly we got these two, T38, 391. Okay, and now we got one more, T117, T138. So you are dividing the data into stratas and then randomly selecting. This is one more method, that is sampling using stratified sampling. And one more technique is for data reduction, data cube aggregation. So the data can be aggregated so that the resulting data set is smaller in volume without loss of information. Here you can see this is sales data, yearly wise data. So 2008 data, 2009 data, 2010 data. So for every year, we are storing the quarterly sales. So this is sales data for all electronics branch from the years 2008 to 2010. Okay. Here the sales are given in quarters. So now if you apply data cube aggregation, now you are obtaining the annual sales. Okay. You are aggregating these quarterly sales and then you are collecting the yearly sales. So 2008 total sales, sum of all these, $24, sorry, $2,24,000, okay, 4,08,000, 3,50,000, 5,86,000. All these will be summed and then you will get this amount, 15,68,000. Okay. Similarly, 2009 sales will be aggregated, 2010 sales will be aggregated. So this entire data is represented in smaller volume using this data cube aggregation. Yeah. And the next one is data transformation. So data transformation is also one of the pre-processing technique. So here you are converting the data from one format into another format. You are converting the data from one format into another format. The format of the data is changed. So we have a different techniques called smoothing, attribute construction, aggregation, normalization, discretization, concept hierarchy generation. So all these are different methods of data transformation. So smoothing we already discussed when discussing this data cleaning. In case of data cleaning also we use this technique, smoothing technique, bin by median, smoothing bin by median, bin by mean, smoothing bin by boundaries. There also you're smoothing the noisy data by converting it to some other form, right? So similarly, smoothing can also be applied for data transformation. And next, attribute construction. You're creating the new attributes from the given set of attributes. Okay. So constructing the new attributes from already existing list of attributes, that is attribute construction. And next, aggregation. Aggregation, whatever we discussed previously, data cube aggregation, right? So aggregation can also be applied for transforming one form to another form. And next, normalization. So this topic we'll discuss now. Here, the data will be scaled such that it will fall within smaller range. The data will be converted into a smaller range. The range will be changed. So we'll fit the total data within -1 to +1 or 0.02 +1. So we'll see this normalization techniques in this today's class. Yeah. We have 3 normalization techniques: min-max normalization, Z-score normalization, and decimal scaling. The first one, min-max normalization, will linearly transform the data. Okay, a linear transformation is applied on the original data. So if you have a set of data points for numerical attributes, for numerical values, surely we'll be having the minimum and maximum values, right? So minimum and maximum. These are the minimum and maximum values of an attribute A. We'll consider the minimum and maximum. And next, we will transform each value Vi into another form Vi dash. Vi is the actual data. Vi dash is the transformed data. So the new values will be within the range new min A, new max B. So how to calculate this new value Vi dash? So min-max normalization follows this approach. So whatever the value that you need to transform, that is Vi. So Vi minus minimum value. So this is considered as the minimum value. Next, divided by the difference between maximum and minimum. And next, new max, new min. So what is the range? Whether it is -1 to +1 or 0.0 to +1. So what is the new maximum, new minimum? That will be considered plus new minimum. So this, if you apply this, then the actual Vi will be transformed to Vi dash. Let's see an example. Yeah. So here you have income attribute. So income attribute. And here I have not listed all the income values directly. You were given the minimum and the maximum. Minimum and the maximum. Minimum and the maximum are given. Otherwise, even for example, you might be given this all the values of income also. All the values of income may be given, and then from that you have to select the minimum of the income and maximum of the income in order to convert a particular data value. Okay, minimum and maximum is given in this question, and then you are asked to map these, map a value within the range 0.0 to 1.0. So this is new minimum and this is the new maximum. So according to this min-max normalization, you're transforming the data $73,600. $73,600. So this is the value for income. So we know income will be having a large number of values. Means the range will be large. Income maybe from 10,000 to even you can have 3 lakhs like that. Okay, the range will be very large. So we can transform this data into a simple form within 0 to 1.0. How to perform this using min-max normalization? So according to min-max normalization, so what is the VI value? 73,600 minus minimum. What is the minimum of this income? 12,000. So divided by what is the maximum value of the income? 98,000. And what is the minimum? 12,000. So VI is 73,600, minimum is 12,000, maximum is 98,000, minimum is 12,000. Into what is the new maximum? New maximum is 1.0. What is the new minimum? New minimum is 0 plus new minimum. New maximum, new minimum, new minimum. So if you solve this, you'll be getting 0.716. So this is according to min-max normalization. So the income 73,600 is converted to 0.716 based on the input values of the income, based on its minimum and maximum. Okay, based on the values present in that income, you're transforming this $73,600 to a new range, new value called 0.716. The new range is 0.0 to 1.0. So in this way, large range of values can be mapped to or transformed to smaller range of values. And next one is Z-score normalization, or it is also called as zero mean normalization. So here the values for an attribute A are normalized based on the mean, that is average, and standard deviation. Okay, based on the mean and standard deviation, we'll perform this Z-score normalization. So if VI is the input that is to be transformed, the output is VI dash. So how we calculate the Z-score is, so VI dash is equal to, so input, what is the original input? VI, that we need to transform. What is the mean of all the values present in attribute A? A dash. So standard deviation is sigma A. So this A dash and or A bar and sigma A are the mean and standard deviation. Okay. So we have to know the mean value and standard deviation. Previously in min-max, we used the normalization. We have applied that based on the minimum value and maximum value. Here, the Z-score, we are considering the mean and standard deviation. Yeah. For example, in the same problem that we have discussed previously, if you are given the mean and standard deviation, this is not possible always. You might be receiving a list of attribute values. Then you need to calculate your mean and standard deviation. But in this question, you are given this values, both standard deviation and mean. Mean is $54,000, standard deviation is $16,000. So now Z-score normalization, using that, the value of this 73,600 is converted to, what is the value, new value that is obtained? 1.225. Okay. So it is transformed to a smaller value. So in previous min-max normalization, we need to find out the minimum, maximum, and also we need to know the new minimum and new maximum. But here, new minimum and new maximum are not required. We'll just find the mean and the standard deviation. Yeah. One simple technique for normalization is normalization by decimal scaling. So normalization by decimal scaling. Okay. First, I'll explain you the example, then we'll go to this formula. So we have the values of A in the range minus 986 to 970. Okay. Yeah. So what is the maximum absolute value of this A? Maximum absolute value is 986. Absolute value is 986. Okay. So to normalize using this decimal scaling, we have to divide each value by, what is that value you need to divide? So that minus 986 normalizes to minus 0.986 and 917 normalizes to 0.917. So for that, you need to divide each number with 10 power 3. You need to divide each number with 10 power 3. Okay. So if you divide each number with 10 power 3, that is 1000, then minus 986 will be normalized to minus 0.986 and 917 will be normalized to 0.917. Okay. So here, yeah. So it normalizes by moving the decimal point of the values of the attribute A. So by moving the decimal point of the values present in the attribute A, this normalization is done. So the number of decimal points moved, it depends on the maximum absolute value of A. So what is the maximum absolute value of A here? 986. Okay. So we are moving the decimal point to 3 digits. Decimal point to 3 digits. 986 means 986.0, right? So you are now moving the decimal point to 3 digits. So based upon the maximum absolute value, if you consider here, you may say that 917 is the maximum value. But we are saying that considering the absolute value means there may be negative values. So considering the absolute value, we have to find out the greatest number and then we need to move the decimal point based on the greatest number. Okay. Yeah. So now coming to this formula. So Vi is the original value. Vi dash is the transformed value. That is normalized value. So it will be normalized to Vi will be normalized to Vi dash by dividing it with 10 power j. By dividing the original input with 10 power j. What is the j here? J is the smallest integer such that maximum of the resultant value will be less than 1. Okay. So what is the maximum of Vi dash here? Maximum of Vi dash is maximum of minus 0.986. That is it should be less than 1. It should be less than 1. In such a way, you need to select the j value. So j value is selected in such a way that the resultant of this, it should be always less than 1. Okay. So in order to convert this minus 986 to 917, what is the number to be used for division? So what is the number? So if you apply, for example, if you consider j as 2, if you divide this 986 by 10 square, so what is the value that will be getting? 9.86. It is greater than 1. So if you divide with 10 power 3, then you will be getting 0.986, which is less than 1. Why we say this as maximum is, even we can divide 986 by 10 power 4. The value will be less than 1, isn't it? If you divide 986 with 10 power 4, then you will be getting 0.0986. If you divide with 10 power 5, you get 0.00986. So among all these 0.0986, 0.00986, 0.986, which is the maximum one? Maximum one is 0.986. Have you obtained this? By dividing the 986 with 10 power 3. By dividing 986 with 10 power 3. So we select j as 3 in our problem. We'll select j as 3 in such a way that this criteria is matched. So you may be confused with this. What is this maximum of Vi dash less than 1? So for that I am explaining this. Okay, so what is the absolute value? So absolute value means you'll be getting the positive value. Yeah, okay. See, what are the values? Minus 986 to 917. So simply divide it with 10 power 3. 10 power 3. What is the value that you'll be getting? 0.986, 0.917. Why to divide with only 10 power 3? Why can't I divide with 10 square? If you divide with 10 square, you will be getting 9.8, 9.17. These values are greater than 1. But what we are saying, the values should be less than 1. Okay, then I'll divide with 10 power 4. What happens? You will be getting 0.0986. Here you will be getting 0.0917. Okay. But among all the values, you need to select this 10 power in such a way that the maximum value must be less than 1. So in our case, if you select j as 3, you will be getting 0.98, 0.91. If you select j as 4, you will be getting 0.098, 0.091. If j as 5, you will be getting 0.0098, 0.0091. Okay. So what is the greatest number among all these? You can consider any value. The value goes on decreasing, right? If you consider j, if you increase the value of j, the value of the resultant value will always be decreasing. So what is the maximum among all these? 0.917, 0.986. So what is the j value that is to be selected? 3. J is 3. So this is decimal scaling approach. It is actually a simple approach. By seeing the values itself, you can say the new value. No need to calculate any mean, median, or standard deviation, anything. So you need to understand this criteria. That's why I explained you in order to understand. Okay. It looks simple actually. To divide with 10 power 3, we'll be getting a value that is less than 1. What's the matter? Then you have to understand this, right? So that's why I explained. Okay. Next. Yeah. Number of j is equal to number of digits in the largest value. Yes, that we can say. But mathematically, we have represented it using maximum of vi dash is less than 1. So mathematical representation is that one. So theoretically, we can write in any way the number of digits in the largest value. Simple. But mathematically, if you want to express that, that is the notation. Maximum of all the values for this new value vi dash must be less than 1. Okay, Manish, do you understand? Yeah. Next one is discretization. So this is also one of the technique for data transformation. So it is the process through which we can transform the continuous values into a discrete form. So continuous values means you will be getting all the list of values, continuous data, right? So if you can't count all the possible list of values, then we call it as a continuous data. Discrete data means fixed number of values will be there. Okay, so we can transform the continuous values into discrete form using this discretization technique. So it will transform the numerical data by mapping them to some interval labels or concept labels. Example, if you have the age attribute, you can map them into interval labels such as 20 to 39, 40 to 59, 60 to 79, or conceptual labels. These are the interval labels, or even you can use the conceptual labels such as youth, adult, senior, etc. So age is continuous values. You'll be having 1, 2, 3, 4. So many values will be there. Okay, so you can discretize them into interval labels or some conceptual labels. So we have different discretization techniques. So one is a discretization by binning. Discretization by binning. We know the binning technique, right? Okay. So this is top-down unsupervised splitting technique. So we call it as top-down approach. So which is the unsupervised splitting technique. So how we are going to split is based on the given input. What is that input? Number of bins. Okay. So here for binning purpose, we are not using the class information of the tuples. So we call it as unsupervised discretization. So unsupervised, why we call it as unsupervised is we are for every tuple, we are not considering the class label information for discretization. Okay. But it is based on the user specified number of bins. The input must be given. Okay. It is sensitive to the user specified number of bins, and also there is a possibility of outliers. Okay. If outliers exist, then this technique may not discretize properly. If outliers exist in the input data, then discretization will not give the accurate results. Yeah. See here. We have the values from 1 to 23. You can see here the values from 1 to 23. Now you're considering the bin interval. So bin interval is considered as 4. Number of bins can be given, or the interval, bin interval can also be given. So bin interval is 4. So means 1 plus 4, 5. So 1 to 5 will be 1 bin. Next 6 plus 4, 10. 6 to 10 will be another bin. 10 to 15, 16 to 20, 21 to 25. Okay. So in this way, you are performing the discretization. So for the first 4 data points will belong to the first bin, next 6 data points. Next, in the third bin, we have 10 data points. In the fourth bin, we have 13 data points. In the last bin, fifth bin, we have 9 data points. Okay. So this is the discretization by, 1 minute. So this is a discretization by binning. So no need to use the class information of that entire tuple for splitting. Simply based on the bin interval or the total number of bins, we are sorting the data and then dividing the data based on the each bin size. Okay. And we may have the values with the different frequencies. So one bin may be having some small number of data points, another bin may be having some large number of data points. Okay. Yeah. And the next one is the discretization by histogram analysis. So yeah, histogram analysis is, it's also an unsupervised discretization technique, as it do not use the class information. So here also we'll partition the values of the attribute into different buckets or bins. Yeah, this technique I already explained you. In histogram analysis, we have seen in case of data reduction, we use this histogram, right? So the continuous values will be divided into, will be divided into multiple buckets or bins based on, we have equal width histogram and equal frequency histogram also, or equal depth histogram also. So histogram analysis is one more technique for discretization. Means it will partition the attribute values into disjoint ranges. And the next technique is discretization by cluster analysis and decision tree analysis and correlation analysis. So we'll discuss in the next class. We'll discuss in the next class, and then I'll start the next topic, that is frequent pattern mining, so which is one of the important concept in your data mining subject. Okay. Any queries? Okay, students. Yeah, we'll meet on next Wednesday.